in Christ, we find out who we are and what we are living for. Long before we first even heard about Christ and got our hopes up, as we heard about how cool it is, how great it is, how amazing it is to serve Christ, before we first heard about Christ and got our hopes up, he had his eye on us. He was looking at us. He had designs on us for glorious living. Part of the overall purpose he's working out in everything and everyone. So you are part of this grand plan that God has for what he wants to do on the earth. So it's in Christ that you find out who you are and what you're living for, what he's called you to do as you work together with him for the purposes, to accomplish the purposes that he has planned for the earth, that he's working out in everything and everyone. So I think that's pretty cool. Hope you do too. Anyway, all right, so what we're going to talk about here are these addition reactions. So remember, we have in our carbon-carbon double bond, we have a sigma bond and we have a pi bond, right? And we said that the sigma bond is lower in energy. So if it's lower in energy, it's stronger. We said the pi bond is higher in energy, and so it is a weaker bond. And so if it's a weaker bond, that means we can use those electrons for reactions. And so the reaction that we're going to see in this chapter is the addition reaction, where we have this atom A and this atom B, and they get added to the two atoms of the double bond. So we had a double bond here, a double bond between these two carbons. And so one carbon gets A and one carbon gets B, but we're using the electrons in the double bond and also the electrons in the bond between A and B in order to add them across the double bond. So A and B gets added to the atoms of the double bond. So when we're talking about these reactions, remember when we think about reactions, we have to think about delta H. And remember, delta H, we need it to be negative. And so what was delta H? It was the sum of the DH values for the bonds broken minus the sum of the DH values for the bonds made. And so remember, for this, delta H has to be negative. If it's not negative, then we can't do the reaction. All right. So as we talk about our first of these addition reactions, it's the catalytic hydrogenation. We already talked about the hydrogenation, right? We looked at that where we were taking an alkene and turning it into an alkane. We saw that last chapter. So now as we talk about it, we just said, oh, we have some catalysts. Now we're going to be more specific. One of them is palladium on carbon. So not just palladium, but palladium on carbon. Platinum, so Pt2O. And then nickel, which is called rainy nickel, or written like this, RaNi. So these are the catalysts, some common catalysts for this hydrogenation, where we take an alkene and we turn it into an alkane. And so remember, this is hydrogen gas and then some kind of a catalyst. So here are the examples of catalysts. So if we didn't have a catalyst around, this reaction would take decades, years, centuries, whatever. And so we have to have a catalyst to speed up the rate of the reaction. So the catalyst acts by activating the hydrogen. And so it reacts with the hydrogen, so we get these hydrogen atoms bound to the metal catalyst. But just for your information, methanol, ethanol, acetic acid, ethyl acetate, these are all good solvents for this hydrogenation reaction. But let's look at this. We have our catalyst surface, so whatever the catalyst is, the palladium, platinum, nickel, whatever, but that's the metal surface. And so in the presence of hydrogen, that hydrogen bond, so remember this is H2, that bond will break between the two, where now we'll have the two atoms bound to the surface of the catalyst. And so with those two atoms bound to the surface of the catalyst, the alkene comes in, and the alkene will also get an association with the catalyst surface, where now it's close, it's brought in close, where we can add one of those hydrogen atoms to one of the carbons of the alkene. But if we do that, remember, this carbon has an octet, and so if we add a hydrogen and its electrons, notice where the bond is starting, in the middle, where the arrow is starting, in the middle of the bond, and it's pointed to the carbon, that means that we're bringing in a hydride, right? What's a hydride? Hydrogen with a lone pair. And so we're bringing in a hydride to that carbon, which means it's going to have too many electrons. So look at the arrow here. from the middle of the double bond now to the surface of the catalyst, where we've now made this bond here. And so with that, now we can use the electrons in that carbon catalyst bond to add to the hydrogen, where now this is a proton, and then the electrons get pulled in to the catalyst. We regenerate our catalyst. The catalyst gets regenerated, and now we have added in 2 hydrogen atoms to our carbons of the double bond. This is an addition reaction. So for this addition reaction, how are the hydrogens added? Well, the hydrogen atoms both get added to the same face of the alkene. We would call this a syn addition. So remember, when we're talking about these carbons of the double bond, remember that they are trigonal planar. And perpendicular to the molecular plane, we have our p orbital. So the p orbital is perpendicular to the molecular plane, which means that we can add above and below. So what are we doing? We can, for a syn addition, both of the hydrogens get added above, or both of them get added below, as opposed to an anti-addition where one would get added above and one would get added below the molecular plane. But we have a syn addition for hydrogenation. So remember I said, stereochemistry matters. This is a part of stereochemistry because this makes the hydrogenation reaction stereospecific. The hydrogenation reaction is stereospecific. The hydrogenation only occurs by the syn addition. So we are only adding both the hydrogens to either the top face of the alkene or the bottom face of the alkene. So we'll learn more about anti-addition, but this is our syn addition. So for this reaction, we are looking at here, this alkene, and it's in a ring, 1-ethyl, 2-methyl cyclohexene. So the ring has the alkene in it, but hydrogenation, we see our platinum catalyst and then ethanol as the solvent for this reaction. But we get these 2 products. And so with this reaction, we can add our 2 hydrogens either above, and so here, notice they're both as wedges. And so if the hydrogens are both wedges, then the ethyl and the methyl are now on a dash line. And then they've drawn this other side so that you can see this mirror plane here. And so if we get this mirror plane, you know that this is the non-superimposable mirror image of the one on the other side, which tells you that these 2 are racemic, right? These 2 are enantiomers of one another. But on the other side, we would have the hydrogen. If we pancake flip this molecule over here on the right, let's pancake flip it over. And so as we pancake flip it over, you can see that we would have the hydrogen on the wedge, hydrogen on, on the dash line, and on the wedge we would have the ethyl. And then on the other side for the methyl, we would again get the hydrogen and the methyl on the wedge. So they've pancake flipped it over, but what we're seeing here is these 2 enantiomers. So these 2 are enantiomers of one another where the hydrogens each get added to the top. And so if they get added to the top, they're both wedges, or they get added to the bottom where they would both be on dash lines, which forces the other thing to have the opposite, right? So if the hydrogens get added as a wedge, then the ethyl and methyl have to be as dash lines. If the hydrogens are dash lines, then the ethyl and methyl are on the wedge. Because remember, if we have a tetrahedral carbon like this is a tetrahedral carbon, we know that tetrahedral carbons, one of the bonds is a wedge, one of the bonds is a dash, and then the other 2 bonds are within the plane. So never draw this where you have 3 bonds in the plane, 1 wedge, 1 dash, and then 2 bonds in the plane. But anyway, we have this hydrogenation where we can have the hydrogens added above and below the molecular plane, And so we get this racemic mixture. We get a mixture of enantiomers here. Questions on this hydrogenation? All right, so as we have been talking about, this alkene, we have a pi bond in there, right? We have these 4 electrons shared between 2 carbons. 2 of the electrons are sigma electrons, and 2 of them are pi electrons. And so with these pi electrons, they are polarizable. And so we can polarize, right? We can move the electrons over to one atom or the other. And so we can use our alkene as a base or as a nucleophile. As a base or as a nucleophile. So remember, we've seen this kind of thing before with our oxygen atom with lone pairs. We can use that to attack an electrophile. We're seeing the same thing here. When we have an alkene, so carbon, carbon, double bond, if we have some kind of electrophile, so something with a positive charge, partial positive, we can attack the electrophile. And so when we attack the electrophile, we can add it to one of our carbon atoms. But when we add it to one of our carbon atoms, the other one ends up with a positive charge. So we have our arrow from the middle of the carbon-carbon double bond to the electrophile. We add the electrophile to one of the atoms of the double bond. And so then the other atom ends up with a positive charge. This is called an electrophilic addition. We're adding an electrophile to the double bond. An electrophilic addition, we add an electrophile to the double bond. So what are we seeing here? Remember, this red area is an area of high electron density. Why is it an area of high electron density? Because we're sharing 4 electrons. We have 4 electrons between these 2 carbons. So it's a lot of electron density in a really small space. Like charges repel, electrons repel one another. They don't want to all be in 4 of them in this tight space. And so we can easily break that bond, use those electrons to pick up an electrophile. So here's an electrophilic addition. The electrophile can be a proton. The electrophile can be a proton. So if we have here our alkene, so we see our area of high electron density, and we have a proton, right? Proton has no electrons, so an area of low electron density. We go and pick up that proton and we add it to one of our atoms of the double bond. And so we add it to one of the carbons, which gives us now an area of low electron density on the other carbon. We have a carbocation. And so with our carbocation, as long as we have some kind of a good nucleophile around, the good nucleophile can trap that carbocation. So the nucleophile attacks the positive charge, where now we have added H, X, to the double bond. We've added a hydrogen and some kind of a halogen in general to the double bond, so a hydrogen halide. So remember, when we're talking about HX, we know that that's a strong acid, right? As long as X is chlorine, bromine, iodine, right? Fluorine, HF, that's not a strong acid. But we have a strong acid. Is it nucleophilic or non-nucleophilic? Remember, it's nucleophilic. It's a nucleophilic strong acid because we end up with a nucleophile, right? X with a negative charge after we do this reaction. So let's look at an example of this. Here we have cyclohexene, and with cyclohexene we have HI. So I'm going to draw it out because when we want to do a mechanism, we know we want to draw it out and show lone pairs. But remember, for this acid, electrons are being pulled toward iodine, right? Iodine is more electronegative. So where do I start my arrow? From the middle of the carbon-carbon double bond, and it ends at this hydrogen that is acidic. Remember, these 2 carbons are sharing 4 electrons. It's an area of high electron density. And so in the alkene, we can use that as a nucleophile to attack this proton, or as a base, really, to attack this proton. But when we attack the proton, Something has to happen to these electrons, so we break that bond. And so we end up with this intermediate where, remember, we don't have to show where the hydrogen is, but we do need to show that there's a positive charge. And so we've added a hydrogen to, if I number this 1, 2, here, how many hydrogens on carbon 1 in the beginning? We have 1 hydrogen on carbon 1 and 1 hydrogen on carbon 2 in cyclohexene. In our intermediate now, we still have 1 hydrogen on carbon 1, but now we have 2 hydrogens on carbon 2 in our carbocation intermediate. And so we have this positive charge, so something has to have a negative charge. To balance that out, it's obviously going to be our iodide. And so then that can attack the positive charge, which gives us this product. So remember, we don't have to show this hydrogen, it's assumed there. So we could just draw this product like this. But they are showing it so that you see hydrogen gets added to one atom and iodide to the other. Those 2 atoms, so carbon 1, carbon 2, that were the double bond. So we have to use a nucleophilic strong acid. And remember that that is HX, as opposed to a non-nucleophilic strong acid. Remember what those were? H2SO4, H3PO4. Those are non-nucleophilic. So that's not going to work here. A non-nucleophilic strong acid won't work here because we need to add in our nucleophile, right? We need the nucleophile to be the iodide, chloride, or bromide. But remember, when we have a nucleophilic strong acid, so here we have a nucleophilic strong acid, we're going to draw out the bond for the mechanism. But when we have a non-nucleophilic strong acid, we can just write H+ for the mechanism. If we were using a non-nucleophilic strong acid for something. All right, so here's our electrophilic addition. So here, the 2 sides of the double bond are the same, and we're not making anything with any kind of stereochemistry, right? We're not making a chiral carbon. So if we started off with this cis alkene, or we started off with this trans alkene, let's look at what the reaction will do. So with this cis alkene, we draw arrow from the middle of the double bond to the proton, and then we have the chloride leave. And the same thing over here, middle of the double bond to the proton, and chloride leaves. And so what are we going to get in this reaction? We get this, this hydrogen being added. So if we number this 1, 2, 3, then we get the hydrogen added to carbon 3, where carbon 2 is a carbocation. Here, if we did the same thing over on the other side, we can number this 1, 2, 3. Then again, we have our hydrogen added to carbon 3 and a carbocation on carbon 2. So looking at this, I'm going to draw this in a different way for our intermediate. This is our carbocation intermediate, right? 1, 2, 3, 4. So with our carbocation intermediate, it doesn't matter if we start off with cis-2-butene or trans-2-butene, we're going to end up with the same intermediate. They are identical, right? You saw that from how I numbered it. Carbon 1 is a methyl, carbon 2 is a carbocation, then we have an ethyl after it, right? Carbons 3 and 4. So they are identical. So I can draw it in this way that I've drawn it here with the zigzag pattern. And then also they are achiral. There's no chiral carbon here in this carbocation intermediate. So they are identical and achiral. There's no chiral carbon here for this intermediate. And so with the intermediate, the chloride can attack the top or the bottom of carbon 2, right? The top face or the bottom face. We have this empty p orbital on carbon 2, empty p orbital on carbon 2 that can be attacked from the top or the bottom. So remember, the carbocation is trigonal planar. Perpendicular to that plane, we have an empty p orbital, and that empty p orbital perpendicular to the plane, the trigonal planar carbon 2, we can attack from the top or the bottom. So if we attack from the top or the bottom, or we can say front or back, we're going to end up with these two products. So one of the products will have a wedge for that bond, and the other product will have a dash for that bond. And so here, if you did the, if you looked at this, so you can do this later, this is R and this is S. Going back to chapter 5, you should know how to do this to assign the configuration. But what is the relationship between these two? These two are enantiomers of one another, right? Non-superimposable mirror images. So we can say that this is racemic. We get a one-to-one mixture of these two. It's equally likely that the chloride will attack from the front as it is that it will attack from the back. Or we can say the top and the bottom. Equally likely, there's no difference there. And so we get this mixture of enantiomers. So cis and trans, the alkenes will end up with the exact same intermediate, identical intermediate. And if we started with trans 2-butene, we'd end up with racemic 2-chlorobutane. If we started with cis 2-butene, we'd still end up with racemic 2-chlorobutane. It doesn't matter the starting material. We're going to get the same mixture of products here. It doesn't matter the stereochemistry of the starting material. And so if it doesn't matter the stereochemistry of the starting material, we can say that this is non-stereoselective. Non-stereoselective. We're going to get the mixture of enantiomers here. This is non-stereoselective. It doesn't matter if we start off with cis or trans. Questions here? So here we have a different starting material. So with this starting material, we have an achiral starting material. And in these steps, we're going to actually end up with a mixture of diastereomers. A mixture of diastereomers. So when we do this, let's look at the steps here. So I put it up in the top. This is still the same slide. I'm just going to draw this out a little more clearly for you. So we start off here with our alkene, cycloalkene, with 2 methyls. And so here we're reacting it with HCl. And so from the middle of this bond to the proton, because it has a partial positive, and then middle of this bond to the chloride because that has a partial negative. And so what are we making in this reaction? Well, in this reaction, we're going to be putting a positive charge on one of these atoms. And so we have a methyl with a positive charge. But in this reaction, we're also going to be putting in a hydrogen. And as we put in the hydrogen, we're going to be making a chiral carbon. And so we can have this, and we can have this. These two are our intermediates, our carbocation intermediate. So remember before, when I showed you this one, I said this is achiral. But now this is chiral. This intermediate is chiral. And we get these two things that are enantiomers of one another. So I'm going to write racemic here between the two, which tells you that we get a one-to-one mixture of these two carbocation intermediates. They are enantiomers of one another because we have a chiral carbon here that we've created. And so we get a mixture of enantiomers. Another way to draw this, if I want to show the hydrogen, you know the hydrogen's there, but I'm going to draw it out just so that you can see what we're doing in the end here. But what we're going to have here, so again, I'm just showing the exact same thing, but I'm just showing you the hydrogen that's on this carbon with the methyl. Right? If we have something that's a wedge, we have to have something that's a dash. And so in one case, I have a hydrogen on the dash line, and on the other case, I have the hydrogen on the wedge. This is really what you're seeing over here. This is the exact same thing. I'm just showing you the hydrogen so that you can see where the hydrogen got added. But you should know, this is how you should draw it, but you should understand that this is what's happening. So I'm drawing it out so we're all on the same page. All right, so now we have our chloride, negative charge, which can react with either of these carbocations. It's a 1-to-1 mixture of the two. And as it's a 1-to-1 mixture of the two, chloride's around and it's going to react with all of it. So as it's reacting, though, we're going to get this mixture of products. So one of our products, and I'm going to show you the hydrogen so that you can see where the hydrogen was added. But again, we don't have to show that. So if we had our hydrogen here on a dashed line, what happens at the other carbon is that we can have our chloride also added on a dashed line, which means that the methyl has to be on a wedge. And then we can also get this product where now we have our hydrogen on a wedge and a methyl on the dashed line. And we have our chlorine added on a wedge as well. And then we have another product where we have our hydrogen that was on the dashed line and our methyl on the wedge. But now with the chlorine gets added to the wedge and that methyl ends up on a dashed line. And then we have just our last possibility, which is our hydrogen on the wedge and our chlorine on the dashed line. So we have these 4 products that can form. Starting with these 2 carbocation intermediates, we can have our chlorine adding from the top or the front, which would be the wedge, or the bottom or the back, which would be the dash. And so we have these 2 different products for each of the different intermediates that we had. So what's the relationship between these 2? Well, these 2 that we have are enantiomers, and so I can write racemic over the 2 of them. We have a 1-to-1 mixture of these 2 products. And we have a 1-to-1 mixture of these 2 products. But it's not 1-to-1 of the 2 racemic mixtures. Of the 2 racemic mixtures, we actually get a 40% yield of this product and only an 18% yield of this product. But of the 2 products, it's a 1-to-1 mixture. So of the one that's 40%, 20% is one product, 20% is the other. Of the product that's 18% racemic, 9% and 9%, okay? So 1-to-1 mixture of the 2 products. But among these are diastereomers of one another, right? This and this, these are diastereomers. And any other combination. So what's the difference in these? Well, the difference here is that both the hydrogen and the chlorine got added to the same face here. And so this is a syn addition. That's why I showed you the hydrogen, so you could follow me here as you see the hydrogen that got added in the first step and the chlorine that gets added in the second step. They both get added to the same face. Versus this other product where hydrogen and chlorine, one's on a wedge and one's on a dash. So this is the anti-addition product. They got added to opposite faces. So it ends up that the syn addition is the major product. I guess I'll say major products, because we end up with that racemic mixture of the 2 products made by the syn addition in a higher yield. Why do we have the 2 products made by the syn addition in a higher yield? Because notice that we're adding this large chloride. So here in this step, we're adding this large chloride here to an atom that is 1 carbon away from a chiral carbon. Is it easier for the chloride to come in on the same face as the methyl or on the same face as the hydrogen? It's easier for the chloride, the large chloride, to come in on the same phase as the hydrogen. So the syn addition is favored. The syn addition is favored because we allow for the chloride to come in on the same phase as the hydrogen versus the chloride having to come in on the same phase as the methyl, the larger methyl atom. So our syn addition, we end up with a higher yield here of our syn addition versus the anti-addition, but each of these products, because we have a chiral intermediate here, because our intermediate is chiral, we end up with a mixture of diastereomers. Going back, when we had an achiral intermediate, we ended up with a racemic mixture. So really a one-to-one mixture, optically inactive product, right? Optically inactive product, a one-to-one mixture of just these two enantiomers. But because we are introducing another chiral carbon in the course of the reaction, or if there is a chiral carbon already present before the reaction, right? If there's a chiral carbon already present somewhere else in the molecule, that would also lead us to getting a mixture of diastereomers for our product. Questions on this? So for this reaction, it's non-stereoselective, but it is regioselective. So the same reaction is regioselective. So when we're doing the reaction, we've just been looking at symmetrical alkenes. So going back, we had an alkene where we had a methyl on one side, a methyl on the other side. There's no difference in the two sides, right? There's an internal mirror plane here. This is totally symmetrical. But what happens if it is not symmetrical? Well, the reaction is regioselective, where the hydrogen is going to go to the less substituted carbon of the alkene. So when we do this reaction, so let me redraw this. This is our starting material here that we see at the top. Here we have HCl. And so when I draw this arrow, it doesn't tell us where the hydrogen goes, right? I said the hydrogen is just going to be added to one of the carbons. So if I call this 1, I call this 2, 3, it's just going to be added to either carbon 1 or carbon 2. So if hydrogen gets added to carbon 1, then carbon 2 ends up with a positive charge. If the hydrogen gets added to carbon 2, then carbon 1 ends up with a positive charge. I don't have to show the hydrogen that got added. I know it's there because this is 352 and I've been doing this for a while, right? So we have these two different options for the carbocation intermediate, which would lead to two different products, either this product or this product. And it turns out that this is a regioselective reaction, and so we only get this product, and then we get none of this product. So this is our correct product, only this, none of this, where it got added to carbon 1. The hydrogen gets added to the less substituted carbon of the alkene. And so the hydrogen would get added to carbon 1 of the alkene because that is less substituted. So same here, we have these 3 carbons, 1, 2, 3. So we could add it to carbon 1 or carbon 2. We add the hydrogen to carbon 1 and we add the bromine to carbon 2. Same with this. We have here, we'll call this 1, we'll call this 2. Hydrogen gets added to carbon 2 because it's less substituted, and the iodide gets added to carbon 1 there. So this is a regioselective reaction, and this follows a rule called Markovnikovs Rule. Markovnikovs Rule. So what is Markovnikovs Rule? Well, simply we can say H goes where there are more H's. H goes where there are more H's. And so as we said, we have this double bond, carbon 1, carbon 2. How many hydrogens are on carbon 1? We know that there are 2 hydrogens on carbon 1 versus carbon 2 has only 1 hydrogen. H goes where there are more H's, which means that the hydrogen is going to be added to carbon 1. We're going to add it to carbon 1 because we end up with these two different carbocations. So remember the carbocation that we would get here? Either this or this. What's the difference? Well, this is primary versus this is secondary. Which one's more stable? We know secondary is more stable based on hyperconjugation, right? So that means it's going to be lower in energy versus going to primary, which is higher in energy. So the stability of the carbocation intermediate is going to dictate the regioselectivity. So regioselectivity, the reaction happens in a certain region. H goes where there are more H's. So the hydrogen will add to carbon 1, which makes carbon 2 the positively charged atom here because H goes where there are more H's, and we end up with a more stable carbocation. So we're going through a transition state that is lower energy because we end up with a lower energy secondary carbocation. We know that the reaction is going to go through the lowest energy transition state in order to get to product. So even though the difference in energy of the products is about equal, there's not really a lot of difference in energy of the products. There is a large difference in the energy of the transition states. And so if there's a large difference in energy for the transition states, that's going to reflect the product mixture. So we're not going to go up to form our primary carbocation because we know that is very much unstable. Questions on that? All right. So in this reaction, you know that we are adding hydrogen. So here from this bond, we attack this hydrogen, this red hydrogen, and our leaving group leaves. And so H goes where there are more H's. So I know I'm going to put a positive charge on this carbon. A positive charge on this carbon. And with that, we have a secondary carbocation. We know that hydride shifts and alkyl shifts, they are possible whenever we make a carbocation. And so can we make something that is equal in stability or more stable than our present carbocation? Yeah, we can make something more stable by a hydride shift. So notice this arrow from the middle of the bond to the carbon. From the middle of the bond to the carbon. And so then I end up with a positive charge here on this atom now, where I have a tertiary carbocation. We know this is our most stable of our carbocations. And so look at the product that we formed. So I color-coded this so you can see, okay, H goes where there are more H's. We added our hydrogen. If we call this 1, we call this 2. We added our hydrogen to carbon 1. But carbon 2 could be either a carbocation here. So this would be from this carbocation. This carbocation would lead to this product where our chloride added to the positively charged carbon 2 versus this carbocation where our here this is carbon 3, where our chloride added to carbon 3. Notice the yield, 40% yield versus 60% yield. As we do these hydride shifts, obviously, if we're going to go through the more stable carbocation, that's going to be the major product here. So our major product is the product formed after this rearrangement. But we can minimize these rearrangements. They can be minimized by running the reaction at low temperatures. If we keep the temperature low, then we can avoid rearrangements, and also by using an excess of nucleophile. So what does that mean? It means if we were running this reaction, we would have HCl and let's say NaCl, where we'd have just that chloride nucleophile around. So we'd have an excess of the nucleophile. We wouldn't just form the nucleophile from the reaction of HCl. We'd also have more of that chloride floating around. And so that's us using an excess of nucleophile, a salt of the nucleophile. So that allows us to avoid the rearrangement, but here the rearrangement allows us to put that chloride on carbon 3 after a hydride shift. Questions on that? All right, so this is 12-4 now. And so here we're going to talk about Still this electrophilic addition, but with this electrophilic addition, what if we have a non-nucleophilic? If you don't, why do you want to avoid rearrangements? Well, what if you just want this product and you don't want this one? If you want this product that's in 40% yield, you can add in an excess of nucleophile to increase the yield of that product, where the secondary carbocation reacts rather than rearranging to form the tertiary. So it just depends on what you want. But anyway, if we use a non-nucleophilic strong acid, like sulfuric acid or phosphoric acid, then we don't have a nucleophile around, right? Non-nucleophilic, there's no nucleophile around. And so then we can use water as the nucleophile. We know it's a poor nucleophile, but in the absence of anything else better, we can use that as the nucleophile. So this is called an electrophilic hydration. It's also going to follow Markovnikovs rule, so it still has the same regioselectivity and really stereoselectivity as what we looked at before. But anyway, what's our first step? Well, as I said, when we have H2SO4, we can just write H+. And so that's what we have written here, H+. So from the middle of the bond to H+, you pick up a proton. H goes where there are more H's, so we end up with this tertiary carbocation. Stable. And so we don't have a nucleophile around, right? We didn't use HBr, HCl, HI. So there's no halogen around, but we do have oxygen with its lone pair. And so the arrow starts at the lone pair on the oxygen to this carbon, where now we're making a carbon-oxygen bond. And so we end up with an oxonium ion. What do we know about oxonium ions? We know that they're very acidic. And so one of the hydrogens attached to the oxygen, I can write acidic on it, but both of them are acidic. So I put partial positive here because oxygen has a partial negative. Now look at this. Oxygen has a formal charge that is positive. A positive charge formally, but oxygen is always electronegative. And so if it's always electronegative, that means it's always going to have a partial negative. It's always going to be pulling electron density toward itself. When you give oxygen a positive charge, it hates having a positive charge. And so it's pulling electron density away from that hydrogen, giving it a very much partial positive charge, a very strong partial positive charge there, where we are forming now something that's very acidic. We have a very acidic blue proton. So we can draw the arrow from the middle of the bond to the hydrogen, to the oxygen, which gives us a proton. So minus a proton here gives us an alcohol product. So we're starting off with an alkene, and we're ending up with an alcohol in this hydration reaction. What's the opposite of this? Look at these arrows. This is reversible. What if we went back the opposite direction? Well, we would start with an alcohol, and we would go back to form an alkene. What do you think that reaction is called? Well, we know that reaction is a dehydration reaction, right? So we have here a hydration going forward, but we can go the opposite direction, a dehydration. That's a reaction that we've seen before, our dehydration of alcohols in order to yield the alkene. But this is following Markovnikovs rule. We are doing this hydration, ending up with an alcohol in this reaction. But as I said, we have our hydrations, alkene hydration. We're adding water to the double bond. So sorry, just to go back, we added water to our double bond. So one of our atoms of the double bond ended up with OH, and the other one ended up with one of these hydrogens. And so we're adding to the double bond, we're adding hydrogen and OH. So one of them goes to one, and then here we use these electrons to pick up the other. So we're adding water. This is a hydration, adding water across the double bond. So for this hydration, the alkene hydration, we said it's the opposite of the alcohol dehydration. These two are in equilibrium. This is a reversible reaction. We can go back and forth. And so we have to think about Le Chatelier's principle for how do we stay on one side, how do we stay on the other side. Le Chatelier's principle will help. but the acid present is going to be used as a catalyst. The acid present is going to be used as a catalyst. So if we keep the temperature low, low temperatures will favor the formation of the alcohol, but if we have high temperatures, that's going to favor the alkene. We already talked about this, right? High temperatures, elimination reaction. That elimination is going to form the alkene. We talked about this in chapter 9. So for our alcohol, if we have concentrated, so a high concentration of the sulfuric acid, and we have a high temperature, we're going to do the elimination reaction. So E1 or E2 reaction, what we did in lab, to make the alkene. But if we have the alkene and some water around, really in excess of water, and we keep the temperature low, then we can use our catalytic acid to go from the alkene to the alcohol. So this is an equilibrium going from the alkene to the alcohol, alcohol to the alkene, just in the presence of catalytic acid. So if we have an alkene and we have it in neutral water, it's stable, but if we add in some acid, if we lower the pH of the water, then the alkene will begin to react to make the alcohol. So for our dehydration reaction, here we have 2-butanol. When we do this reaction, initially, we're going to get 1 to 1 to 1. For 1-butene, cis-2-butene, trans-2-butene, initially. So in the beginning, we'll protonate the alcohol, get our oxonium ion, the water will leave, and we end up with our secondary carbocation here. And with that secondary carbocation, we have all these hydrogens around. We deprotonate them, 1 to 1 to 1 mixture of the 3 products that we can get here. And so this is because relatively, the relative energy of the transition states are all the same. So relative to one another, the energy of the transition states is all the same, which means that, remember, we have to go over this bump, over this transition state here. If they're all the same, then the energy we add in doesn't matter here. We're going to be adding in the same amount of energy, so we end up with 1 to 1 to 1 mixture of the 3 products. So for this, we would say that initially this is under kinetic control. Initially, this reaction is under kinetic control. So what does that mean? When a reaction's under kinetic control, that means that the product obtained is the one formed fastest. Right? What is kinetics? That's our rate, reaction rate. So whatever is formed fastest, that's going to be what we get as a product. And so we said we get a 1 to 1 to 1 mixture. They're all formed fastest initially because we said the energy of the transition states is the same. So when a reaction's under kinetic control, whatever has the lowest energy transition state, that's what's going to form fastest. And the transition state energies are about the same for all 3. And so we get a 1 to 1 to 1 mixture. But as we continue, if we have some strong catalytic acid around, as we continue with the reaction, so we said initially this is what's happening, but as time goes on, we can go from our alkene back to the carbocation in the presence of acid. We're going backwards now. So we're reforming that secondary carbocation in this reaction. And so as we do that, we end up back here with our secondary carbocation that can then again lose a proton to form the product. So we've let this go longer. Initially, 1 to 1 to 1, but as time goes on, we're going to go from the alkene back to the carbocation because it's reversible. And so we get this rapid equilibration. So we're going from our carbocation to the alkene, and then from our alkene to the carbocation, and then back to the alkene, and then back to the carbocation, and back to the alkene, back to the carbocation, over and over and over again, as we are protonating and reprotonating, deprotonating and reprotonating. And so as we do this reaction, we end up with an equilibrium mixture where now the most stable product is the major product. And so we know it's not 1 to 1 to 1, right? We know trans 2-butene is going to be our most stable, and so this is our major product. And so we end up getting more of this product, trans 2-butene, over time. Initially, we had all three, but we know that these two are minor products. Excuse me. We know that our terminal alkene and our cis alkene are minor products. And so with time, more and more of the alkene will form the of our carbocation will form the trans 2-butene, and less of the terminal and the cis alkenes are going to be formed. And so we would say that initially the reaction is under thermodynamic control, where just whatever's formed fastest, that's what forms. But then the reaction is under thermodynamic control, where now the product obtained, as we let the reaction go, we get our thermodynamically most stable product. So the product obtained is most stable. So instead of it having the lowest energy transition state, now it's going to be the lowest energy product. The lowest energy product. So our lowest energy product is what we form as we let this equilibrate. So in the equilibrium mixture, as we let the reaction go, we get more and more of our product that we would expect, which is our trans 2-butene, our lowest energy product, rather than just the lowest energy transition state. They all basically have the same transition state energy, but the energy in product, that is what is different. So if that's true, then we can use this procedure to take something that is a less stable alkene and turn it into a more stable alkene isomer. So if we just have catalytic acid, so H2SO4, H3PO4, just a catalytic amount, just a little bit of it, we can take a di-substituted alkene, turn it into, H goes where there are more H's, so we turn it into this carbocation here. H goes where there are more H's, so we know we have some acid around from here to the proton, so we end up with a CH3 and a tertiary carbocation that can then form here this tri-substituted alkene. So we go from di-substituted to tri-substituted. We know that that's going to be more stable just by doing this equilibration. We can go from cis to trans. And so from cis to trans, here we have these T-butyl groups. I'll write it out as they've written it. And so if we have H goes where there are more H's, there's no difference here, right? They both of these carbons with two hydrogens, with one hydrogen. And so I can turn this one into a carbon with two hydrogens. And I have my positive charge here. And so I go from my cis, making a carbocation, and then I can deprotonate to make the trans product. So I go from cis, which is less stable, to trans, which is more stable. Questions here?
Why does it only take on one hydrogen? Why not take on both and fill both of those carbons with hydrogens?
We could do that when we have H2. But if we have acid, we only have one hydrogen around, one proton around. And so that's all we're going to do there. We're just going to add in that proton because we're using this as a base, right? This is a base. This double bond is a base. And so what do bases do? Bases just pick up one proton. So we're polarizing the electron density, moving it toward one of the carbons of the double bond and using that carbon as a base. So that picks up a proton. So the other one ends up having a positive charge.
Yeah, quick question, Dr. Narbanian. So a few slides ago, we saw that like we used H2SO4 for like making the alcohol, and I just wanted to ask a question. Usually, like even in chapter 9, we learned that you usually use PCC, CHCl2, or like CH2Cl2, or like H2SO4.
PCC is oxidation.
Oxidation. So that's what I was asking because
that's turning an alcohol into an aldehyde or a ketone.
Which is my question, because over here we saw that we turned a double bond into an alcohol, but in chapter 9, we saw that we can use actually H2SO4 to make a ketone. So I was getting confused.
No, you're talking about, so just because acid is around doesn't mean that you're going to be doing the same exact reaction. So here we're taking an alkene, and in the presence of H2SO4 and water, we're turning it into an alcohol. Then we can go further and do an oxidation with the alcohol, turning it into an aldehyde or ketone. But it's not the same reaction because we would have an oxidant around in order to do that oxidation. We'd have PCC, or we'd have potassium dichromate or sodium dichromate, Na2Cr2O7, along with the H2SO4 and the H2O. So because those three things are together, that's going to take the alcohol and turn it into an aldehyde or ketone. But here, we don't have an oxidant around, so all we can do is turn the alkene into the alcohol. Other questions? All right, you guys. Well, that's where we'll end today. So we finished 12-4. We're going to start 12-5 on Wednesday. So make sure you're going back over this, doing your homework so you can see the sections that we've done. Reread this, do the homework, add to your notes more things from, your reading. If you have questions, remember we can bring those up in office hours this week. But yeah, have a good day, you guys. Enjoy my birthday. Go out and enjoy it. God usually gives me like beautiful weather for my birthday, so enjoy that. That's God's gift to me, but I'll give it to you guys too. And I'll get that stuff graded for you as quickly as I can. All right? Have a great day. You guys, love you. Thank you for all the birthday wishes. I love you guys. Bye.
Can you go back to the kinetic control side really quick?